All right, so at Intel, we do a lot of systems programming, and we work with a lot of partners who do as well. So we care a lot about making systems programming better. So what exactly do I mean by systems programming here? Well, the broadest definition would be roughly anything that isn't an app. But more specifically, I want to talk about things like BIOS and firmware and bootloaders, operating systems, kernels, embedded, and similar types of low-level code. I want to talk about virtual machine implementations, the foundation of the cloud. And I'm going to include web browsers in this because they're more than just an app themselves. They're a platform for websites and for web apps. So systems programming makes many demands on programming languages. And systems programming, because of that, needs both capability as well as safety. So to talk about what I mean by that, I want to go into a little historical advancement in systems programming. So this pattern of advancement applies to many different types of systems. But let's look specifically at BIOS, at firmware, and at bootloaders. So all of these things were originally written very heavily in assembly language, long after other software wasn't, with some extensions, with a small smattering of assembly. But in general, C worked its way down the stack. And now even the BIOS is written almost entirely in C with a little bit of assembly here and there. So what exactly made that move possible? C wasn't new. C had been around for decades, and BIOS and firmware and bootloaders and other system software was still using assembly language heavily. So what is it that made developers comfortable moving over to C? What eventually happened to make the developers of BIOS, firmware, bootloaders, and other system software comfortable with that move? So in order to make that move, they had to be confident in two different ways to switch from one programming language to another. First of all, the language has to be sufficiently compelling, to have sufficiently compelling features to warrant moving in the first place. It can't just be a little bit better. It has to be substantially better to warrant the effort and engineering time needed to move. Now, C had a lot of compelling features to offer assembly developers. It provided some degree of type safety, at least enough to not easily mix integers and pointers. It made developers more productive with higher level constructs, with more readable code. But just as important as that, the language also has to provide parity. Developers had to feel confident that C was no less capable than assembly language. It can't just be better, it also has to be no worse. This is the criteria that gets developers kicking and screaming. You'll pry assembly language from our cold, dead hands. So how did C measure up to assembly exactly? Well, you could do almost anything with C. It was just as fast in the general case with a good compiler. It could express any kind of data that assembly could. And it had an escape hatch. You could still move to it incrementally and do anything you want in assembly and combine that with C. So as C, with a few extensions to C, got sufficiently capable to achieve parity, and as developers got more confident in that parity, the developers of BIOS and firmware and bootloaders all moved over to C. So those are the two ways that developers need to have confidence in a language before switching to it. It needs to have sufficiently compelling features to make it worth switching, and it needs to have parity with no less capability than what it replaces. So at this point, systems programming uses C almost everywhere by default. Assembly language is what you reach to only if you absolutely have to. And there are use cases for it, but by default, you do systems programming in C. Well, C is very much becoming where assembly language was years ago. C is the new assembly. There are many, many calls to move from C to higher level languages. Developers want that both because of problems with C that can't be fixed, and features in other languages that they really want to use. Now, I want to take a second here and emphasize, I'm not just talking about buffer overflows here. Better than C is about a lot more than that. Too many discussions about C never get any further than that. Now, don't get me wrong. Buffer overflows are older than I am, and it's an embarrassment to the industry that they still exist. But memory safety is the bare minimum requirement these days. Not having to deal with manual memory management is the basic expectation for any higher level language than C. Any language that wants to be better than C has to offer a lot more than just protection from buffer overflows if it's actually going to be a compelling alternative. So people care about usability. They care about productivity. People care about writing code that is more self-explanatory, that accomplishes more work with less code. But while I said this wasn't just about buffer overflows, that and a lot of other security issues are also critically important as well. And the nice thing is usability and productivity go hand in hand with security. They help you bring better security as well. The less code you need to write to accomplish something, the less chance you have of introducing bugs, security bugs or otherwise. Beyond that, are there languages that have sufficiently compelling features compared to C to make people want to switch? Absolutely. There is an extraordinary array of high-level languages available today, and we could spend an entire talk on any one of them, an entire talk on one feature of one of them. Almost any language that you reach for is going to have powerful and expressive features along with unique features specific to that language that make it great for specific domains. We have an embarrassment of choices these days. Many languages flourish for applications. Applications can also more readily make trade-offs. They can sacrifice capabilities they don't need for features that they do want. They don't necessarily need the full capabilities of C, and they're happy to trade those capabilities for any number of compelling features, for better security, for better productivity, all sorts of things. Meanwhile, systems programming continues to demand parity with the full capabilities of C. And very few languages can claim parity with C other than C itself, and that's a big reason C sticks around. Now, this is something we care about. We want systems programmers to be able to use high-level languages too. So what would it take to have full parity with C, to be no less capable than C? What would it take for a language to work anywhere that C can work? So I'm going to be talking about this from the perspective of the Rust language, and I want to emphasize something really important here. This talk is not about convincing you to use Rust. This talk is not about evangelism. Convincing you to use Rust might well be a side effect, but it's not the primary point. Instead, I want to talk about what are we doing to achieve full parity with C, to make sure that Rust works anywhere that C can, to make sure that you can choose Rust for systems programming if that's your choice. So to do that, I want to cover first a brief history and overview of the Rust language to give you an idea of the key ideas that make Rust matter. I'll cover some of the existing features that provide parity with C, including some that are unique to Rust. And then I'll go through what we're doing specifically to achieve full parity to make sure Rust can do anything that C can and beyond. So first, let's start with a bit of history. Rust was started at Mozilla Research to build a safe, high-performance programming language for large, complex systems, like, say, web browsers. Now, pretty much every modern language offers automatic memory management, so you don't have to manually call free on every object. Most modern languages do that by having a garbage collector running in the background. They watch for when you stop referencing an object, and then they free that object. One of Rust's key features is that it has automatic memory management without having a garbage collector or a runtime system of any kind. Rust has a system of declaring whether any given use of an object is the owner of that object or whether it's just borrowing that object temporarily. And if you're just borrowing an object, the compiler will keep track of that. It'll make sure that the original sticks around as long as you reference it. Rust makes sure that the owner of the object frees it when it's done, and it inserts the call to free at compile time with no extra runtime overhead. So in C, these are things you usually track manually. It's not that you don't care about these things, it's that you have to care about these things yourself. In a C library, you'll usually have documentation, or you hope you have documentation, that tells you that a given function returns a brand new object that you need to free when you're done, or that it returns a reference to the middle of an existing object, and you need to not free it until you're done with the outer object. And if you get those details wrong, you get a memory leak, or you get a double free that introduces a security hole. So this is a big part of what Rust provides as a system to track for you what other languages typically make you track manually. Not having a runtime is a key requirement for any language that wants parity with C. When a language has a runtime, you cannot easily use it for systems programming. You have to initialize that runtime before you can call any code. You have to use that runtime to call functions. And the runtime itself might run extra code behind your back at unexpected times. So a little bit more history. Mozilla uses Rust to develop Servo, which is a high-performance browser engine. They then integrated the ideas and code from Servo back into Firefox in a project called Quantum. They also jokingly call that development process Oxidation, since it adds Rust. And a big part of what they're doing here, in addition to safety, is building safe concurrent programming. They want to run as much as possible in parallel to more effectively use all of the cores that you have. For example, they find what CSS styles apply to which elements of your page in parallel, because it's a complicated process, and you want to be able to handle that for a large page, not just on one core. Then they render different parts of the page in parallel, and then glue all the results together onto one rendering into the screen. That is incredibly hard to do correctly, or safely. They have to keep track of which thread is doing what work, which thread touches which objects might have interdependencies between each other. Other browser engines have tried to do that, have made efforts to do that in languages like C and C++, and have been unsuccessful at it, largely because of the complexity of introducing concurrency into these processes. But the same features that make Rust safe for memory management also help keep track of which thread owns which object, and which objects can be passed between threads, and which ones require acquiring locks. So because of that, they were able to safely build a concurrent browser engine. So the same properties that make Rust work well for Mozilla to build a browser engine also make it appealing for many other companies and projects that are building large, complex systems. So that includes a lot of companies that you already know, many companies that are represented here even. Microsoft, Google, Facebook, Amazon, Dropbox, Chef, Fastly, Baidu, a huge number of companies beyond that. You can find a long list online, and hundreds of companies are using it to build all sorts of different software. There's a lot more to it than that. So Rust actually has a long and interesting history. It was started 4 years ago today, in fact. This is the 4th anniversary of Rust 1.0, the stable release. It was started years before that. And beyond that, for those last 4 years, it's been the most loved language on Stack Overflow. People always say, well, I've started using it, and I want to keep using it. It has the most loyalty in that way. Beyond that, there are a lot of published security studies about the properties that Rust provides. This isn't just a thing that they advocate as, oh, you should use it because it has these properties. There was a study from Microsoft saying that 70% of security bugs are memory safety issues of some kind, and exactly the same type of issues that Rust fixes. And a number of developers from Microsoft expressed interest in driving those types of security fixes using Rust. Mozilla did a study that showed that if they'd written one component of Firefox in Rust from the beginning, they'd have avoided 73% of its historical security issues. They went back and looked at every CVE in that component and said which of them would still have existed and which of them were fixed by writing it in Rust. Okay, so this gives a lot of compelling features for people to choose Rust for a project. But let's bring this back to what it would take for people to actually make that switch. It's not just about the sufficiently compelling features. People also need to be able to choose Rust, which they can only do if it has enough parity with C for their particular application. And for some kinds of low-level systems programming, Rust doesn't have enough parity with C yet. So I want to talk about the existing capabilities of Rust that do provide parity with C. And in the process, let me give you a little bit of my personal history working on Rust, because achieving parity with C is exactly what got me involved in the Rust project in the first place. So one key aspect of parity with C is interoperability with C. People use C because it can call any C library. It can be called by any C code. And Rust can mostly do that. Rust can call C functions or provide functions C can call. Rust can build structure types that are compatible with C. It can work with raw pointers to memory in the process. And that's often used as part of wrappers around C code, in which you then build a higher level, safer API on top of that. So my first contribution to Rust was to round out that support by teaching Rust about C-compatible unions. I wanted to build a virtual machine in Rust, and the Linux kernel interface for that, dev-kvm, required unions. Rust didn't have them, so I wrote an RFC, a request for comment, to change the language to add C-compatible unions. I worked with the Rust community and with the language team to get unions into Rust. And because of that work, I'm actually now part of the Rust language governance team, helping to evaluate and guide other changes into the language. And this particular area of C compatibility tends to be my primary area of interest. So another example of this, somebody at Intel mentioned they wanted to write a library to intercept certain functions for debugging, for graphics specifically. Some of those functions took C-style variable argument lists. So I ended up writing a proposal to get support for that into Rust, and the development work for that is being finalized and going into the language right now as we speak. I also added support for unnamed structures and unions, which is a widespread C compiler extension that made its way into C11. People use that to lay out complex structures in memory, and Rust needs to interoperate with that. I care about filling in the corner cases, filling in the gaps, to make sure that you can call or be called by any C code. So as a result of that, one of the things I want to announce is that I'm starting a working group, the FFI working group, whose charter is to achieve full C parity, including common C compiler extensions used in systems programming. I'm working with other developers at Intel and other members of the Rust community to develop both the specifications for the remaining features that we need, as well as the implementations of those features. And not only that, one key part of that charter is we want to support systems programming using stable releases of Rust, not just experimental nightly releases of the compiler. So that means that we aren't just adding new features, we also need to evaluate some existing experiments and build consensus on the right path forward. We also want to make sure that systems programming features are as safe as possible, sometimes even safer than the equivalent in C whenever possible. For example, the C version of varargs requires that you manually set up, enumerate, and tear down those arguments. The equivalent version in Rust will actually help you manage some of that. You still have to get the details right for which arguments you have, but you don't have to remember to call end when you're done. So as another example of that, we care about the ability to build small binaries without any extra overhead from unused libraries. Now that's possible today using a nightly Rust compiler. I was able to build a Rust hello world that compiles to 504 bytes without too much trouble at all. But that needs to be possible using stable Rust, not just using nightly Rust. That's going to take changes to the build system. That's going to take linking changes. It's going to take changes to how Rust handles its standard library when you don't actually call all of that library. Apart from that, systems programming often needs low-level details of the processor, such as privileged instructions. Rust has support for inline assembly today, but it's only in the nightly compiler, and it's only using the existing error-prone inline assembly syntax that C uses. So we're collaborating on a proposal right now to develop a more robust syntax for that and get that on the path to stabilization. Inline assembly would give you almost all instructions you want by writing assembly directly. But right now, you can access almost any SIMD instruction by using a built-in intrinsic function. So that makes it possible to write highly optimized compute algorithms. And there are several libraries in the Rust ecosystem that already use that, including high-performance search algorithms, for example. So we're working on enhancing the Rust compiler so that it can help understand when your processor supports those instructions so that you can't accidentally call an intrinsic that your processor doesn't have the instruction for. This will make it safer and easier to use SIMD intrinsics. There's also a new floating point format available, bfloat16, which is available in the latest Intel hardware. It's designed to minimize the storage space and the memory bandwidth used by floating point numbers. It's used in libraries like TensorFlow that work with huge sets of data like neural network weights. And it's designed to be a chopped down version of the 32-bit format so that it's very easy to interoperate with existing systems, existing functions, existing storage. So I'm working on adding support for bfloat16 into Rust so that you can use the full capabilities of your hardware. So a lot of other things we're adding that make it easier to work with systems linking requirements like symbol visibility, weak symbols, symbol aliases. We're adding more aspects of structure layout, including C-compatible bitfields and an offsetof mechanism to compute field offsets. So with that in mind, I want to give a summary of what we're trying to work on. We need full parity with C to support the long tail of system software, and we have a Rust working group working towards that goal. And every feature that we add covers more of the space of systems programming. We want to make sure that all developers have a choice of languages, not just app developers, but systems programmers as well. And nobody is stuck with only one language that will do what they need. So we want to make sure that no matter what language you're using, C or Rust or anything else, that it runs best on Intel hardware and that it gives you access to the full capabilities of your hardware. And we would love to have your feedback to help drive what C features that we add to Rust next. So please do get in touch if you want to do systems programming in higher level languages.